Hey, good morning, everyone. We're going to be looking at section, what is this, 7.1, day 2 on our calculus trainer today. And today is all about the slope field. And what that means is it's a graphical way of looking at the differential equation and the solution of the differential equation, which doesn't require any integration. So this method is really good, especially if you have a function which is not integratable. Oftentimes, in order to access the particular solution, mathematicians will use a method such as the slope field method. So let's kind of take a look at what we're looking at here with the next screen. And we're going to be using Quidditch a little bit here for our, our context. So consider the Quidditch pitch. I just didn't even realize that I would need to explain what Quidditch is at this point, but maybe that's a possibility. But Quidditch is basically that wizarding game. It's kind of like soccer on broomsticks, so you can just think soccer if you want. So consider the Quidditch pitch as a two-dimensional plane with x's going between -3 and 3 and the y-coordinates going from -5 to 5. The goalposts are going to be set along the lines y equals -5 and y equals +5, and the midline will be at the x-axis. And for the sake of discussion, we're not going to talk about the altitude of the broomsticks. We're just talking about their coordinates on the xy plane. So basically, we're taking an xy plane and we're putting it on top of a soccer field, and we're saying, well, position is based on the xy plane. So we're going to say that Harry's movements along this plane is going to be governed by a differential equation, dy dx equals x plus y. That's important for us because that is going to tell us the change in his y-coordinate with respect to the change in his x-coordinate. So first observation here is that we can't solve this differential equation using our current techniques of integration. Okay? Our current techniques of integration in Calculus BC or in Calculus AB would be to separate the variables, and just a real quick distribution of the variables here kind of reveals to us that it is going to be impossible to solve so that we have all the y's on the left side and all the x's on the right side. So this is not differentiable or integratable using what we currently know in calculus. Not to say that this differential equation can't be integrated. It can be integrated, but we're not going to learn how to do that in Calculus BC, certainly. You're going to have to probably wait till you take a differential equations class in college before you can tackle this differential equation. So we can still get an impression of Harry's flight path with a graph of the differential equation, and the graph of a differential equation is called a slope field. So I kind of want us to start thinking of the slope field as nothing more than the graph of a differential equation. So let's take a look at how we're going to do this, and the way that this is typically done is to go ahead and figure out the slope at a few different point coordinates. So I've created what would you call this? A matrix, I guess, a chart here with all the x coordinates and y coordinates that we're going to consider. So over here, for example, we have x equals -3 and y equals -5. If the differential equation is x plus y, then -3 plus -5 is -8. And over here at -3 and -5, okay, the slope would be -8. Remembering that the slope is the same thing as dy dx. So I know this is a lot of coordinates to calculate for, but it does kind of go fast. It usually goes fastest if you keep, one of these two variables constant. For example, here, I'm going to say negative on the -4 row. I just have to say -4 plus -3, that's -7. -4 plus -2, that's -6. -4 plus -1, that's -5. -4, -3, -2, and -1. When you go across like this, you could also do the same thing going vertically down the columns as well. But when you do that, then usually you will see a pattern form here. Let's do the next line so you can see what I mean again. -3 plus -3 is -6. -3 plus -2 is -5. -3 plus -1 is -4. -3, -2, -1, and 0. So real quickly here, you're seeing this pattern. -8, -7, -6. Of course, this is going to be -5, -4, -3, 2, -1, 0. And then now just to make sure, we've got a -2 plus a +3, that's 1. So the pattern is still going to hold here. This is going to be -4, etc., etc. So go ahead and fill that out. I'll give you a minute or so. Or push pause so you can fill out the rest of this chart. This is what it should look like when you're finished. The patterns here are very strong. You can see a pattern both horizontally and vertically. And yeah, well, there's not a whole lot more to say to that. It shouldn't have taken you a whole lot of time to do this. And you can be rest assured that if you were actually going to do this on an AP test, you wouldn't have this many coordinates to do. I've probably somewhere between 5 and 8 coordinates are typically what we see on the AP test. So don't feel like there's going to be a big time waste on the AP test. It's just going to be a lot less coordinates. So now that we have done this, we have the slope at all of these coordinates. The graph below, this is what you would see on an AP test, is a coordinate plane with a bunch of very, specific places for you to compute the slope. So, for example, at the coordinate -3, -5, we're supposed to plot a small segment that has a slope of -8 from the table. What do you mean from the table? Oh, up over here on this table. -3, -5, and I think I've already highlighted that. -3, -5 is right here, and it has a slope of -8. Okay. Let's pick another coordinate here. Let's pick, 4 on the y-axis and 3 on the x-axis. So the coordinate of 3, 4, the slope is going to be 7. Okay. Okay. There's some tips over here like aiming the segment but basically you're going to get a coordinate that has the slope that we got in the chart. So we said previously that at 3, 4, the slope is 7. So here's 3, 4 right here. Let's see, 1, 2, 3 across, 4 up. Here's 3, 4, and the slope is going to be 7. And what I mean by aiming is, if you take a look, 3, 4 over here, and we want to make a slope of 7, let's use the draw tool. I think that's going to be helpful. If I draw a slope of 7 over here, that means I can't look at a point on this side over here. I got to look at a point on the left side of that because I don't have any other place to look. So 1, 2, 3, 4, 5, 6, 7. So a coordinate with a slope of 7 is going to have a pitch that kind of looks like that. So I'll just go ahead and kind of trace along here about what that would look like. And you don't want to make these segments too big, just kind of enough to fill about half the space in between there. So that looks like a slope of 7. And we're going to do a bunch of these. Let's pick another one. Let's pick -2. What was that? -2 and 2. -2, comma 2. What would that slope be? Well, you can go back up to that chart, or you can remember you're just going to add, but that's going to give me a slope of 0. So -2, 2, that's going to give me a slope of 0. Okay. -3, 3, that's also going to give me a slope of 0. And in fact, sometimes it's good practice just to figure out all the places where the slope is going to be 0 and do those first. Those are usually pretty easy to find. So here the slope is 0 all the way down that diagonal, slopes of 0. Okay. Let's do another couple of points. Let's figure out, for example, -3 and 4. -3, 4, we have the slope equal to, well, what is that? -3 plus 4, that's -1. Okay, so at -3 and 4 up, we've got a slope of -1. Let's use my aiming device to figure out where that is. -3 and +4, and let's swing this around. So this would be a slope of -1, something that follows that pitch right there. So I'm going to go ahead and make a line that follows the pitch of my little helper line. And there we go, slope of -1. Now, if you remember the pattern from the chart up here, you remember that as we go left to right, the slope is going to increase by 1 unit. So starting over here, this was a slope of -8. And go over here, this should be a slope of -7. So why don't we go ahead and figure out a slope of -7 here. And okay, so we're going to put our little aimer over there, and let's go up 7. 1, 2, 3, 4, 5, 6, 7. I probably, I admit that this might be something that's difficult to do on an AP test, but, use your pencil and kind of aim things the best you can. So there's a slope of -7. Let's move across, and the next one should have a slope of -6. So let's give this a slope of -6. There we go, slope of -6. The next slope is -5. Next one is a -4 slope. Let's figure out a slope of -4. Let's see, 1, 2, 3, 4. Slope of -4. Slope of -3 is coming up next. Here's my slope of -3. And lastly, a slope of -2. Okay, there's my -2 slope, and we're done with that row. Okay. Notice how the pitch of this generally, or the slope of this is, tending toward getting more and more positive as we go from left to right. So take a few minutes and do the rest of these. I'm going to pause the video and I'm going to do the rest of mine. And we'll see you in a couple of minutes. So go ahead and pause it here. Fill out the rest of these slopes. So I've got mine finished now. And what's interesting here is you see this wonderful kind of swirling pattern that's going on here with this differential equation. I hope you can see it, that as we go from left to right, if we're above, well, maybe the first thing we should say is, although I said it was important to put this, all of the slopes equal to 0, what is striking here is just below that, all the places where the slope is -1 kind of forms a diagonal line. And that diagonal line, and I'm going to go ahead and highlight that for you. Let's look at this diagonal line right here. When you see that form, that's actually indicative of an asymptote, a slant asymptote. So solutions to this differential equation are going to bend toward that slant asymptote. Okay, what else is interesting? Notice as we go from left to right, of course the slope does increase, but look at the shape it kind of makes. It kind of bends and curves upward. Down over here, it's kind of a similar thing too, although it curves downward away from the asymptote. So, very interesting things here. Let's look at the slope field wisdom. A slope field of the size we just created, of course, is much larger than any slope field that you will create for the AP test. You're not even going to create a slope field this size for one of my tests. This is just for instructive purposes. Now, a typical slope field on the AP test is going to contain less than 10 points. Asymptotes, like we were just talking about, is going to be indicated by slopes that are aligned into a line. So the example above contains a slant asymptote. We have already highlighted it. And as we read from left to right, we're going to start close to the asymptote. If we are above the slant asymptote, we're going to start close to the slant asymptote and then bend our way upwards. And if we are below the slant asymptote, we're going to again start on the left side close to the slant asymptote and then bend downward away from the slant asymptote. We'll see that over here. Now that we have our particular solution, now that we have our slope field, we can see what a particular solution would look like. So, this is where the slope field starts to look and maybe behave a little bit like a magnetic field, if you are familiar with that from physics, or any kind of field in any discipline. This is that field. So to estimate a particular solution, you're going to start at the initial condition, and this is the quote, you're going to go with the flow. You want to read slopes from left to right. If slopes get more positive, so should the slope of the solution curve. And if the slopes from left to right get more negative, then the slope of the solution curve could get negative also. Important, solution curves will not cross an asymptote. They will just continue to get closer and closer to that asymptote without crossing. As a solution approaches the asymptote, the slope will approach the same slope as the asymptote, and the initial condition will affect the shape of the curve in relation to the asymptotes. So we said over here that above the curve, as we read from left to right, if you're above the slant asymptote, you will bend away from the asymptote in the upwards direction. And if you are below the asymptote, you're going to bend away from the asymptote in the negative direction, downwards. So we'll see over here, Harry's best mate, Ron, starts the big Quidditch match at a location suggested by the coordinate -2, -4. So this is Ron over here, -2, -4. While Harry starts the match at 2-0. Why is Harry in midfield and why is Ron all the way at the bottom? Well, Harry's a seeker and Ron's a goalkeeper. I forgot the goalkeeper's name is in Quidditch. So we're going to use a slope field to approximate their flight paths. And if we look at Ron's initial condition, he is far away from the slope field. There's not much to go for on the right side. We remember what we said down over here. As we go from left to right, the slope should get more negative. So that is why you see this part getting more and more negative. Now, as we go that means if we go from right to left, the slope should become less negative. So this is bending to be less negative and approaching the slant asymptote. So that's what's happening with Ron. Let's take a look at Harry. He is over here, and I'll do his slope field equation. We'll do his in green. Notice that since he's on this point, we know that the slope here should look something like that. Now, as we go from right to left, the slope should get more and more positive. So we start to see the slope of the solution curve, get more and more positive. Be careful not to go vertical, because it's probably not going to go vertical. And this is, on the right side, what we would expect, getting more and more positive. Now you might say, well, why does it have to be that steep? Can't it be less steep than that? And you'll notice that as we cross over here, where the x-coordinate is 4, I think, 1, 2, no, where the x-coordinate is 3, we got to maintain a slope similar to what the slope is over here. So any less steep than that, and then I'm going against the slope field. Now, as we go from left to right, we're going to get less negative. So less and less negative. Notice where I am. I am at x equals positive 1.5. And as I go to x equals 1, my slope better be 0. Because that's where my slope is 0. And then I'm going to bend toward the asymptote, and eventually the slope is going to match that asymptote. We're not going to cross that asymptote. We're just going to get really, really close to that asymptote and stay close to that asymptote. Perhaps something like this. Okay. We're matching the slope of the slope field at all of the points we're at, and we're keeping to mind that as we get close to the slant asymptote, we are bent along its path. So this is a pretty good looking curve. This is just approximate, so don't feel like there's a real, someone's going to be measuring and saying, oh, your slope is supposed to be 1.5. Your slope is actually 1.6. No one is going to do that. Okay, you just need to be following the flow of the slope field. That's what I'm going to say about that. So there's our slope field equation. And we are here at important ideas about the slope field. And really not a whole lot to do here. The slope fields, of course, is using the differential equation to plot slopes at usually integer locations on a coordinate axis. Although you can imagine that using technology, you don't actually have to be constrained to those integer coordinates. You can give an approximate shape for particular solutions. If you have an initial condition, you just kind of bend along to the way that the slope field is going. So important tools for estimating particular solutions. The slope field is an important tool for estimating a particular solution when the differential equation is non-integratable. Okay, so this is why we have it. We have slope fields particularly for non-differentiable or non-integratable solutions. Now there's some practice here. We can kind of do a couple of these points. Let's see. For this one, the slope is going to be 2 times the x-coordinate times the y-coordinate. So real quickly, we know that we're going to have a 0 slope if either the x or the y is 0. So any place where the x-coordinate and the y-coordinate is 0, we'll put a 0 slope. That's going to be nice. Notice how that does form an asymptote. Horizontal asymptote there. But this is not an asymptote. It's just places where the slope is 0. Okay, that's good. Let's see. Let's go across where the y-coordinate is 1. So if the y-coordinate is 1, then we got 2 times -3 times 1. That is -6. So let's just draw a very negative slope here. Let's do 2 times -2 times 1. Well, that's the slope of -4. This one gives me an opportunity to do a little bit more aiming. This should be a slope of -2, 0, and then over here on this side, we have 2 times the x-coordinate, which is 1, multiplied by the y-coordinate, which is also 1, and that's going to give me a slope of 2. Ooh, a slope of 2, and then a slope of 4, and then a slope of 6. I think I underestimated the pitch here. And yeah, that's how we're going to do it. And we'll just continue there. Okay, that gives me this slope field here, and I don't know if you can see it, but this kind of looks like a parabola. I don't know if you can see it. Of course, any solution is not going to cross the asymptote at x equals 1. Let's draw our asymptote in red. It's not going to cross this line. I think I said x equals 1. I meant y equals 0. We're never going to cross that line. We're going to get close to it and then move away from it. So that is our first differential equation. Over here, we have a differential equation of x on y negative. So any place where the x-coordinate is 0, we should get a slope of 0. Any place that the y-coordinate is 0, we're actually going to have an undefined slope. So for an undefined slope, technically, well, usually that wouldn't even be drawn. So we're not even going to touch the x-axis because everywhere along the x-axis, the slope is undefined. Okay, let's see. What happens when the y-coordinate is 1? If the y-coordinate is 1, then the x-coordinate, or the slope, is going to be -x over 1, which is just a negative x-coordinate. So if the x-coordinate here is -1, the slope is going to be +1. The x-coordinate here, the slope is -2, so the slope is going to be +2. The x-coordinate here is -3, so the slope is going to be -3, so the slope is going to be +3. And all the way down across there. Likewise, if we take a look at when y equals -2, then the slope is going to be negative of the x-coordinate over -2, which is just half the x-coordinate. So down over here, the x-coordinate is -1. Half of -1 is -1/2. So the slope should kind of look like this. Over here, the x-coordinate is -2. So half of -2 is -1. And then -3/2. And so on down the line. Okay. And we'll just continue and do the rest of these. So here are all of the ones that are suggested by this, and notice how this is kind of a circle. Okay, the slope field here suggests a circle. The last one here, we have the slope is x minus 1, which means that the y-coordinate doesn't matter at all. So for example, when x equals 0, all of these everything where the x-coordinate is 0 is going to have a slope of negative 1. Let's draw negative 1 every place where the slope of every place where the x-coordinate is 0. And if x equals 1, 1 minus 1 is 0, so every place where the x-coordinate is 1 is going to have a slope of 0. Yep. Every place where the x-coordinate is 2, the slope is 2 minus 1, which is just 1. Every place where the x-coordinate is 3, the slope is 3 minus 1, or 2. So let's draw a slope of 2 here. Slope of 2. 2 and 2 and 2. And we're just going to keep going left to right. That's a pretty good looking slope field. One thing you might want to start thinking about is this one we can actually solve. Solvable. So let's solve that one. We get a dy is equal to x minus 1 dx. So the integral of dy is equal to the integral of x minus 1 dx. And so y is equal to half of x squared minus x plus constant. And notice that this is a parabola. Do you see a parabola here in this differential equation? For example, here's a parabola. Notice how it follows along in the differential equation? Maybe I should have done that in a contrasting color. How does that look for a parabola that follows along with the slope field? I'm a little off over here, but that's okay. So this is our differential equation graphs for our slope field. And that's all we have today. So hopefully that was interesting for you. Not terribly difficult, but you probably could use to do with a little bit of practice here. So that's it, and enjoy. Have a good weekend. We'll see you later.